Um, I'm extremely pleased to have John Overton, CEO of Cove, here. What they are doing with memory is like the VMs were doing 20 years ago with the systems. So I think all of you will find this eye-opening. For people who are in the AI or space or even anything that's large computational work, like in capital markets or this, this is incredible capability. So let me just want to introduce yourself.
Yeah, sure. I'll introduce myself. So I'm the founder and CEO of Cove. We've been solving really complex, really some of the most complex challenges in the world for a while. A little bit about myself. When I was in my 20s, I wrote software that was put in 2/3 of the workstation market in the world. About a decade or so after that, I co-invented my first company, distributed hash tables for location service. This is the technology for scaling all cloud storage and all database sharding. We invented that. We now work on memory. Everyone in this building has used software that we either invented or algorithms that we invented. If you've ever used AWS or Google storage, we've got some relationships there. Similarly, if you've ever done a wire transfer of money, which is 93% of the money in the world, that also goes through our software with Red Hat. It is, it's an understatement to say how nice it is to be on the stage with this gentleman. I've known him for a number of years. He's just a class act.
Let's see how well I do. So, when I was when I was at Quant for 30 years, doing big simulation models on all kinds of risk and all kinds of products. The biggest problem I had was loading large volumes of data to do analysis on, but also compute requirements. As memory was very, very expensive, even in the supercomputer. So today's world, particularly with Cove, the memory constraint is gone. And this is, to me, the most incredible thing. I'm actually itching to do something. But, it's also does a lot of other things which John will touch on. But really, from a business perspective, if you're trying to do AI, you don't always absolutely need GPUs. If you're trying to do a big query on your customer base in a bank, that could be half a petabyte of data potentially. This is what you put in memory, and it comes in seconds. When I got to SAP HANA came out. It was an in-memory database. The ERP system, which used to calculate 100, 200,000 calculations overnight, when they put all that data in memory, it was instantaneous. They never pre-calculated anything, and they repeated the calculations over and over again because it was so fast. So this is, to me, the secret sauce of having this virtual memory chain.
So let's step back and see the global picture. I propose that in the history of computing, things move consistently from big and specialized and engineered, highly engineered, to ever so more commoditized. And when they get fully commoditized, they go to virtualized. And that's basically what you see on this picture. CPUs did that with VMware, storage did that, happened with digital, with EMC, networking, and then GPUs. Memory hasn't been done, and it's not for lack of trying. Every major company that I know of has tried to do this for 3 decades. We'll talk about what it is, but we actually have solved that. It's not kind of, mostly academically. It is robustly deployed. It works right now, every day. And we'll show you why that matters in just a moment. Okay. So imagine you have a server, and that server has any amount of memory that you want. Let's say 64 gig for kicks. And let's say you wanted to create a 6 terabyte server. You can take the memory, the virtualized memory, on any x86 server that is produced worldwide, and you can stick that 150 meters away. That's the other side of the building. And it will perform to plus or minus 1 or 2% the same performance or faster than local memory. This sounds impossible. Everybody knows the so-called speed of light, distance of cable problem. An electron travels in a billionth of a second about 10 inches. So how could I introduce, 500 nanoseconds and not have computational impact? We do that all the time. Now that's on one server. The really interesting part is what happens when you think about it more generically. What if I have 10,000 servers? What if I have data centers, campuses of data centers? So anybody know what the cost of memory in a large memory server is? It's 65 to 85% the cost of a server. Anybody know what the utilization rate is of those servers? It's 25%. You know what in AI, you know what the utilization rate in AI of servers? 25 or 30%. And why that is that as you parallelize greatly, if you have one thread or one CE go above the local size of memory, you hit swap. Okay? Anybody know what the cost of swap is? I'll buy the best NVMe drive that you can buy right now and stick it in a server, and a 4-hour job that would take in memory on a regular x86 server will take, if it hits swap, 19 days. Okay? Let it hit you. Days. So I only trade that 1,000 times. What's 1,000 times 19 days? It's not anything that makes sense. If you install us, you can use regular hardware, OpenShift, and Red Hat, and you can make this problem go away forever. And it's real.
So, Cove's SDM, really, and this is a correct term, supercharges OpenShift. You get more performance with no more new hardware. You're able to significantly lower your total cost of ownership, becoming much more efficient. And also, you can access memory from anywhere. It's highly, highly flexible. But I think the most important part from my personal perspective of being an abuser of lots of big systems and machines most of my life is the fact that you're able to do things in memory that you cannot do in a normal machine, even with GPUs, right? And I think that's the sort of sauce. And we have, John will touch on, there's a customer here that's looking at the entire transaction messaging system globally, and they're able to do that on a relatively small environment purely because everything sits in memory.
Yeah, absolutely. Let's give you a little bit of some numbers here. These are not marketing, well, I guess because it's on a marketing slide for marketing numbers, but these are not marketing numbers. These are real numbers. We can validate these, empirically with measurements. In fact, people have all over the world over and over and over. So the 150 meters, that is as real as there is real. You can hide the latency. This is a legitimate, real, shocking customer scenario where someone did something on a popular virtual machine platform, which I'm unable to name, that we might know who they are, and they were running some machine learning jobs. So they ran it and were very pleased. These jobs took 16 hours, and that wasn't really great. So they tried it out on OpenShift plus Cove, and we were 60 times faster, not percentage points, multiples. Okay, so that was kind of so unbelievable because what's the probability you could just download software and use any hardware platform that you've got in your data center and whoop the largest or a very large virtual machine player? So they didn't believe it. So they uninstalled the physical hardware, the metal, in one part in Virginia, and they shipped it to Europe. They uninstalled the virtual machine player and installed OpenShift on the exact hardware that was initially run. They took the hardware from another part of the world, put it together, and they reran it. And it was 60 times faster. Okay, so a 6-hour job down, a 60-day job down to a day. Now, the swap. This is the part that's the most startling because we've all been trained that swap is your smart play. The people who are pushing the edge of computing right now have all learned to turn swap off if I'm doing machine learning. If I have let's say 100,000 threads or CEs or whatnot, and they're all computing up and down, what's the probability that one of those might go 2x, 3x, 4x, 5x more? Well, it's only a data segmentation problem, right? All I have to do is get my data science right, and then it works. That is the state of the universe right now. Right? Really, step back and think about how insane that is. So I'm going to target a quarter of my memory, which is 65 to 85% of the cost, simply because one of my threads might go 2 or 3x or 4x up. What if you could just remap that? Well, obviously, storage class memory. Has anybody ever heard anything in any of the trade backs about storage class memory? It's awesome. It's the best of the best. Oh, and it's 125 times slower than DRAM. Oh, that 4-hour job just took 19 days. Like the numbers, you just don't hit the numbers. That can literally go away. The memory utilization on this, which is also, kind of remarkable. What if you have, let's say, 10 servers, 100 servers, 1,000 servers, and you're using 25 to 30% of the local memory because of the problem I just mentioned? Okay, what's the time to solution for your AI model on that? Okay, what if I could triple that memory, quadruple or quintuple the memory? The other way to say that is my time to solution went from 3 years for a typical production training model, to 1 year or 6 months. Anybody see any business value there? That's what's at stake here. Energy. So one way to look at this is I can use more memory. Another is that I can use efficiencies and utilization rates in CPUs at rates I've never thought to. In fact, we can regularly cut the servers in half. The other way to say that is I've doubled my computational performance. Here's another way. I just cut my power in half. If you're in the European Union and you've got legislated obligations, you can install software, and Red Hat and Supermicro have measured, this is not a code thing, they have measured a 12 to 54% cost reduction in power with no code changes by simply hitting buttons to install software. Okay. Next one. Is this you or okay. Okay. This is we tend to like to undersell the stuff that we publish publicly because the numbers that we get offline are so surprising that they're hard to believe. Like I can put memory on the other side of the building, but let's imagine just following up. I can reduce the number of nodes for the same outcome. I can increase the time to solution in terms of efficiency. I can drive CPU utilization up double or triple. Memory utilization, from triple to quadruple. It is, to say easy isn't loud enough to get a 200% ROI. 500% are numbers that we have seen. If you have a small deployment, let's say 100 some odd servers, all in, it can be $2 million per year per 100 to 120 servers. Anybody got 5,000 servers? Like, let it hit you. It's really real. I think this goes to you.
Yeah, so this is also very important for regulated industries like financial services. Right? So it's, you need to be able to sort of manage your workloads in a very secure environment. You need to have memory that's ephemeral, so it provides, sort of no persistent storage, so it increases your ability to protect your data as well as your models and your IP. And then most importantly, it helps you address issues around cloud sovereignty. We're in a much more sort of volatile world, and sovereignty becomes a big issue outside the US for many countries in Europe and Asia and Latin America. So this is one way of actually, sort of addressing some of those compliant requirements.
So we've kind of hit this a little bit, but this is a quote from the Chief Innovation Officer of Swift that you can see up there. We're going to be able to train the models and monitor the network without any computer or hardware limitations. I want to give a little perspective. That's 93% of the money that goes in the world every single day. It's $5 trillion every 2 or 3 days. We competed against this with Red Hat against the major cloud vendors, and they went with us. One of the cloud vendors said, I'll bet my reputation this is impossible. Test them. They did. The limits of this are every other third-party limit. Your memory addressing limit is the AMD 64 specification. That's a 47-bit address space. I think they're upping that to 53 bits, which I think will push it to 6 petabytes of DRAM, local DRAM per server. This is, I don't know when that's going to be released, but the point is, the limits are whatever the limits of the chip manufacturers, the networking manufacturers, and so on. Yeah.
The only thing I'd like to add is this is fully integrated into OpenShift with an operator. So you have a nice dashboard viewing that you sort of allocate for each project exactly how much memory that project needs. And it can also be automated as well. So it's the use of it becomes incredibly easy across your entire enterprise.
It's provisioned. Think storage provisioning, except eject the word storage from your consciousness, okay? It's memory, it's DRAM, local DRAM. Okay, so if you go over to our booth right over there, you can see a demo of this where a server is operating and doing some machine learning. It has 128 terabytes, and it auto grows into 256. You can do way better than that, but it just shows you routinely. There's also a demo that Swift was kind enough to produce where I think they blow up the memory 20 times or something like this, and it just works from provisioning rules. So there's no effort whatsoever. You don't have to work hard to make this work, is the key principle. Now, is this a you or?
No.
Okay, this is me. So if you don't want to just do software and use your own hardware, you can also buy memory towers. This is a project that we've done with Viking, Sanmina, Red Hat, and Computer Center. So Viking, I believe they do about $10 or $12 billion in sales to the hyperscalers. They're producing these memory towers. You can roll these in, 39 terabytes. It'll be 78 in a couple of months or maybe 6 months. You can just roll them in, plug them in, and then you have data center memory. It all works seamlessly with the OpenShift stack. So like the configuration of this, I think to install our software, to roll this in, install our software is about 30 minutes, and then it works. Then you can a system administrator can apply provisioning rules, and you can govern hundreds or tens of thousands, hundreds of thousands of containers, servers. It all just is built in.